So yeah, do you know how we always had the wrong name when you logged in for the last 3 weeks, I think? That was because I updated. So now I changed the link, but apparently there's 2 links on the website and I only updated one of them, which you all managed to click on the other one, obviously. 50-50 chance. Hey, fantastic. We got everyone in the right meeting now, except for our speaker.
Our speaker.
Let me see. He should be
But
on.
which button we should have supposed to click on?
So I updated the big button on the website, but you all clicked on a small button that I forgot to update.
It's just when you click Neuroccino, it opens the most frequently entered website, and that was from how I was keep using the link to enter. So,
but also the link that is in the calendar was the wrong. You know that you click in subscribe and automatically Google update every meeting that we have in the calendar. So the link in the calendar was wrong too.
Right, we're gonna fix this once we're done with Neuroccino today. Sorry about the confusion. Where is Philip?
maybe trying to enter WhatsApp on his computer. I don't know.
Texting, let me see. Anyone else got a paper they can spontaneously present? Panic.
But everyone is this. These are everybody.
We're missing Team Bordeaux today, except for Anna.
Yeah, because Marcella is in Chile, so she can't join. Chris is at the conference. He can't join, although he's having breakfast right now, so he could potentially join. But it's about the priorities and about the
publicly shame our team members.
No, I'm just jealous. I want to be in Nice as well. I was in Biarritz this weekend. It was amazing, but you know, it looked the picture that Chris just sent into the group. It looked just hey, there's Philip. It looked so good. So I was like, I would rather be there than be alone in the lab. And Michelle is probably bringing the kids to their places they're supposed to be.
Oh, he had physio Monday morning. Broken man.
What did he have?
Physio.
Oh, yeah, it comes with age. Or with our running sessions.
Here, Anna's hosting, so I'm going to hand over to you. Take it away.
Perfect.
Yeah, spontaneous host session. Hello, everyone. Happy Monday. Welcome to Neuroccino, our weekly journal club, the coolest journal club there is out there on the internet. Today, Philip is presenting. The rules of the game are simple. So you can present anything, any piece of exciting science, except your own work. So you can't take your tweet, you can't take your paper, you can't take anything that is associated with you because you want to check out others' work. So Philip, without any further ado, take it away, have fun. And you should be able to share your screen if you're a co-host. Perfect. Steph already took care of it. It's amazing to have the help. Okay, go for it.
Perfect. Can you see my screen? I just shared a link in the chat.
Yes.
And yeah, so for today, I've prepared an article yet again about numerical cognition. The title of this article is Neural Evidence for Procedural Automatization During Cognitive Development. Intraparietal response to changes in very small addition problem size increases with age. So that is mouthful, but I'll try to explain everything piece by piece. So this article is really about the cognitive processes that are involved in the very small addition problems, whose sum are less or equal to 10. So these problems would be 7 plus 3, 2 plus 5, 5 plus 3, 1 plus 2, 1 plus 1, actually, as well. And you might recall in one of my previous presentations, I did a presentation on the neural substrate of numerical cognition about arithmetics. And there were two separate networks, one that were more involved in procedures and in applying strategies to resolve more complicated problems. And there was this other network that was really involved in retrieving arithmetic facts. And I always put this example of very small addition problems that these would be retrieved because we have been practicing them since childhood so many times. So this information is overlearned. But in this article, they really challenge this notion, and these authors propose a different, well, they actually try to validate a different theory that proposes that we actually don't transition to direct memory retrieval, but actually for a subset of very small additions, we might automatize procedures that we use as little kids. So with this general introduction, let's just dive into the article. So imagine that you're in a first grade and you have to solve this very small addition, 2 + 3 = 5.
Philip?
Yes.
Sorry to interrupt you. 1 second. Could you maybe zoom in into your paper
Zoom
a little
in.
bit more?
Okay, yeah.
Yes, because it's a little bit hard to decipher. Perfect.
Can I
Yeah,
zoom in a bit more?
that's
Yeah.
great. That's
Maybe
amazing.
fine.
Sorry for the
If I
interruption.
use that, yeah, no worries. So imagine again that you're in the first grade and you have to solve a very simple problem, 2 + 3 = 5. You would probably use some very slow procedures like explicit counting, 1, 2, 3, 4, 5, or 3 + 2, 3 plus plus 2, 4, 5, and this would be very slow, right? But once you reach age of 10, you probably practiced this problem so many times that you would be able to just retrieve these problems very quickly. Yeah, as I said, because you have been computed these problems so many times. And so there were, from the 70s through the 90s, there were different theories how we retrieve these problems from memory, basically. And these theories try to explain one effect that has been found. Basically, as the problem size increases, also the response times increases. And this is not what we would normally expect, because if we retrieve, then probably we should see like a flat distribution of the solution times. But it has been seen that this is not true, that as the problem size increases, the solution times also increases. And the most accepted model from the memory retrieval perspective put forward this explanation that as problems increase in size, also the overlap between features increase. So there's more interference during the recall of the arithmetic facts, and that's why we see this slope of solution times. But this has been challenged, as I said, by another model that proposes that we transition from slow algorithmic procedures to very fast mental scanning of sequences of numbers. And this model is called automatized counting. It has been actually proposed like 10 years ago. And I'll just show you in what this model consists. So basically, when we are presented with problem 3 + 2, we would like very quickly scan through this mental number line that we have stored in long-term memory, and we would do this scanning even unconsciously. That's also one of the features of this model, that this scanning is unconscious, and we can even confuse it with retrieval. So behavioral studies that try to distinguish between memory retrieval and this fast mental scanning, they are kind of short, and we need more evidence, more neural evidence, and that's what this article is really about. But this fast mental scanning, it has another characteristic, and it operates on the very small addition problems whose sum is less or equal to 4. Why 4? The authors argue that up to number 4, up to 4 elements, we can maintain in this single focus of attention up to 4 elements. They also try to link it to different work and memory theories that we can only maintain and maintain actively up to 4 elements in the working memory. So this fast scanning would only work on problems whose operands are less or equal to 4. Once they surpass this upper limit, we would still use a mixture of more costly procedures such as silent counting or this direct memory retrieval. So behaviorally, what has been done in the past, the automatized counting would predict basically this pattern of reaction times, and the memory retrieval account, the slope would be more continuous. But it's still difficult to distinguish behaviorally between these two theories. But what happens at the so this article is really about what happens at the neural level. And in this article, the authors collected data from young kids, from adolescents, and also adults, and they tried to compare the activity and how the activity either stays constant or whether it shifts. So according to the memory retrieval account, if we shift to a different strategy, probably we should see a shift to different brain regions in comparison to what is the brain regions that are activated in the very young group. And if the automatized counting holds true, then the brain activity, it's proposed that the brain activity should remain basically in the same regions, and it should also increase because it's increasingly sensitive to this automatization. And again, this should be restricted only to problems with operands less or equal to 10. So what they really investigated here was this narrow problem size effect. The problem size effect is, I try to describe here, this narrow problem size effect and how this problem size effect compared in older adults with this very young group. Okay, and whether it depended on the magnitude of the problems. So let's go to the method. I'll try to do this quickly. So in this article, they collected quite a lot for this work. They collected quite a lot of subjects, 149 children, adolescents, and adults. They had 2 separate testing sessions. The final sample, because they had to exclude some subject, was 128. 31 in the youngest group, 31 subjects in 11 to 12-year-old, 26 in the 14 to 15, and 40 adults. They had some control measures like IQ, reading fluency, arithmetic fluency, and processing speed. Each of these really got better with age. And in the third session, they also familiarized the children and adolescents with the fMRI environment in a mock scanner. Then out of the scanner, they did this vocal arithmetic task that involved the 41 single-digit additions. So I'll just show you in the figure what they had to do. They just had to solve single-digit additions. This is actually not what they would be solving because this result 14 surpasses the limit of 10. And they had to give the response orally out of scanner. And inside the scanner, they had to respond with a button press whenever the result came to their minds. And on some trials, just to make sure that the children and adults were solving these problems and not just watching passively, on some trials, the exclamation mark appeared and they had to give this oral response, which was later filtered for the fMRI data analysis. And here you can see how these 2 tasks, one out of scanner, one inside of scanner, correlate on average response times and on this behavioral problem size effect or the magnitude of the slope. So, and they correlate quite highly. So this procedure was quite efficient. And in the scanner, they had to solve in the total of 225 trials. So the single-digit additions were repeated 5 times, just to have enough data. The data were collected with 3 Tesla scanner. This was a resolution of a single voxel. The analysis were done with the SPM. It was quite standard procedure. What really caught my attention is that during the normalization, they normalized all the individual brains into the MNI space. even for the youngest children, because they say that studies have found that anatomical differences between children older than 7 to 8 years and adults are small enough. Yeah, I'm not an expert in this. You can maybe comment on that later. And the final voxel size was of this size. Then for the design matrix, they had 4 regressors, one that coded the very small additions with operands less or equal to 5, one that coded the medium small additions with operands higher or equal to 5, and 2 parametric regressors for this problem size effect within each problem category. And the analysis they did was on whole brain comparisons, where they compared the beta values associated with the parametric regressors, and these were submitted to the second level analysis. So this was done at a whole brain, also with an anatomical mask of the IPS. They say it here, but I'm not really sure if they really done it. This was the analysis that I mentioned in the introduction, the functional ROI that was determined as the brain regions that got activated in the youngest group, and then they averaged the activity within this functional ROI for the oldest group, and they saw whether this activity increased with age, and whether it increased only for the very small additions and not increased for the medium small additions. And additionally, this was not mentioned in the introduction, they also analyzed basal ganglia because they are associated with procedural learning, and here they focused on caudate nucleus and putamen bilaterally. I'm going to show just the behavioral results. On the left side, these are results just to compare with previous studies. And on the right side, we see as the problem size increases, the solution times increases, that's the problem size effect. It actually increases for the very small and also the medium small problems. I have put all the problems here. These are the very small problems. These are the medium small problems. Maybe you wonder why are some of these overlapping. It's because the sum to 6 here consists of problems 4 plus 2 plus 2 plus 4 in the very small category, but here it consists in the medium small category, it consists of 5 plus 1 and 1 plus 5. That would be this point, okay? And it's for, and also you can see how the solution times decreases with age. But behaviorally, we couldn't really say anything about whether this is automatization or this is memory retrieval, because we see a positive slope here in both types of categories. This is just a different representation of what we just saw. I just wanted to highlight that, again, that the solution times decrease throughout development, and that the problem size is still positive for each category of problems in both the vocal task and the sound task in the scanner. And this would be like interpreted in favor of memory retrieval account, because this theory proposes that the automatized counting proposes that we should see only the positive slope in the very small problem category, but here we see it also in the medium small category. They argue against this because this also serves as a more stringent test of the automatized counting theory. So let's see what happens at a neural level. I'm not going to show this to you just yet. So this is the activity that has been the activity for the very small problems in the youngest group. Of course, we see the IPS, and then the medial prefrontal cortex, and then insula. It was activated for both the very small problem category and medium small problem category. And let's see how the beta values increased or not with age. And when the authors combine all the participants and see how the beta values increase, they increase significantly only for the very small problem category. And this increase is not significant for medium small problem category. So this would be interpreted as supporting this automatized counting, because yeah, the regions that initially supported like the slow counting procedures at a very young age still support maybe fast and automatized counting throughout development. But when we really see the activation for each group separately in each of these regions, we don't really see like an increase in activity with development. For example, in insula, the activity really stays the same. In the medial prefrontal cortex, I'm not sure. This is really interesting. And within the IPS, the differences are mainly driven by adults. Even with the adolescents, this activity, this increase seems like non-significant for the adolescents. So the theory of whether we automatize or the solution to this, whether we automatize very small additions, I'm not sure. I think it's still questionable. When we look at the basal ganglia, there are some significant differences. There are no significant differences for the medium small problems and significant differences for the very small problems only in adults in the left caudate. And the authors also argue that this activity increases, but yeah, here probably they don't really say anything about these two groups and whether this is significantly different from 0, and this is probably 0, goes even to negative values. So again, this seems like activity in left caudate is driven only by adults.
Philip, we need to wrap it up so that we still have 5 minutes for questions and a little discussion. Sorry, I don't want to rush you, but if you could like say a couple of concluding sentences.
Great. I will. Perfect. They also do. I'll just comment on this last analysis. They do this last analysis where they saw this is the whole brain analysis, where they try to investigate the increase in activity throughout the age, throughout the development. They saw these 3 regions: the IPS and dorsal precentral gyrus, and these are actually important for the discussion because they say that the IPS supports the mental number line. Whereas the dorsal precentral gyrus corresponds to the frontal eye, may correspond to the frontal eye field, and that is involved in these shifts of attention and this mental scanning. And overall, these authors argue for the automatized counting theory. Also, one of the authors is the authors of the original automatized counting theory account. And yeah, please, if you have any questions, tell me.
Awesome. Thank you so much, Philip. Sorry for rushing you through the discussion. No, if there are questions from the audience, then raise your hands. Ask. We have probably time for like around 3 questions or so. If nobody has a question yet, I can start. Oh, Steph has a question. I don't know if it's me or the other Steph.
Go for it.
Okay. My question is pretty simple. So they looked at kids and they looked at adults. Did they, I don't know if you mentioned it or not, sorry for missing it if you did, but did they account in the procedure of participant recruitment, did they account for like how good people are with numbers? Just in general, because that is a thing, right? Like if somebody is basically talented in numbers and math, whatever, would that somehow influence that?
Yeah, they counted for that by having this control measures, really, this arithmetic fluency test.
All right. Yeah.
Okay. So there was this control measure that they did just to make sure that I think everybody was within the expected range. Yeah. And they really saw that we get better with age, which is expected, but they don't really comment on like individual differences, maybe in this adult group, which would be interesting and probably also important for the theory. Yeah.
Okay, thank you.
Thank you for the question.
Steph, go ahead.
Thanks. So you mentioned that they scanned kids and some of them were rather young. So I was wondering if there's any mention of the difficulties of scanning kids, if they had to train them more, and if that may have also caused some kind of training effect or familiarization effect in the scanner.
They practiced during the first session. I'm not sure how these two sessions were separate in time. But in the first session, they got like familiarization with this fMRI environment and a mock scanner, and they practiced on 25 trials, so the silent arithmetic task in the mock scanner. Yeah, I'm not sure if there would be a practice effect. They also because all the single editions, there are only 45 of them, and they presented in a multiple runs. Yeah, it's there's still the doubt whether there's this practice effect or whether.
But even if they did, then
Yeah.
all the kids did that, right? So
Yeah,
it's
yeah,
not,
that's
you
true.
know, you
That's
kind
All
of,
true.
the kids, but I was wondering, you probably need more for the younger kids than for the older kids. Definitely.
They do mention that they treated the youngest group differently. What is true is that I think they had to discard quite a lot of subject from that group because of movement. Yeah, because they still moved. Yeah.
Thank you.
Eduardo has another question, which is going to be our last one. Deliver. Spotlight is on.
Yeah, it's maybe it's related also to what Stephanie asked, and because you mentioned during the paper that they normalized like the scan from the kids to the standard MNI template, which is not a kid brain. So I was wondering whether 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 they spend a few more words on whether this is actually a good strategy, because they also apply an region of interest set of analysis, and I can see some problems there in,
Yeah, I was wondering whether this should be done. I have no experience with recording fMRI with so young kids. But yeah, I was wondering whether this can like really influence the analysis or the results that they get, and whether it would be more convenient to normalize to more appropriate templates.
whether there are like maybe templates based on younger brains or something.
Yeah. I think there's like this pediatric. I think also in the pipeline that I've used, the fMRI prep, there is a template for younger kids, but I'm not sure for what age they are being used. Yeah. I'm not sure if those are like very young kids or.
Yeah, well, I mean, already like a smaller template would be already better, I guess.
They also say that the functional ROI included all voxels within 6 millimeter radius of each coordinate of interest. So maybe I'm not really sure what this exactly means. If they restricted the beta values, the averages only to the ROI, or whether they would like go outside of this.
Okay, interesting.
Maybe that was just one strategy how to ameliorate this.
Yeah, always tricky with the regional interest.
But a lot of work has been put in this article, like recruiting young kids. Quite a piece of work.
All right. Thank you so very much for the question. Also, recruiting young kids, it's probably, it's a lot of kids of scientists who have to do it, because it's usually like a Max Planck, especially. I know like all the fMRI studies, they're like all with the kids of the scientists. Thank you so very much. That's all the time we have for today. Thanks for all your questions. Thanks, Philip, for presenting this interesting paper. We have another Neuroccino next week, Monday, 9:30, as always. Thanks, Steph, for co-hosting and hosting together. I won't be hosting next week because I will be presenting, but have an exciting week in science, ending it on a on the typical quote of Steph. That's like a trademark now. And yeah, have an exciting and successful week in science, and see you next week, Monday, 9:30.
Good to see you all. Bye.
Good to see you. Bye bye.